On our last lecture on Wednesday, we were talking about the equilibrium constant expression. Okay, how you raise it to the appropriate power using the coefficients in the overall balanced stoichiometric equation. Okay, those who just came in, hurry up. Okay, how to use the Kc expression. Okay. And we looked at the concept of Q. Okay. Alright, so this quotient that we use that can help you determine whether the reaction will favor the forward. If Q is less than K, reaction. Or if Q is higher than K, you will favor the backward reaction. Okay? Right, so like last week I asked you all to post your questions on Slido. So today you can still post your questions all the way back to the end of the week. Alright, later I'm going to address some of the questions that were asked during on Slido. Alright? So what we have found is actually to use QC, alright, to help us predict the direction of a reaction. Right, so I'd like you to consider a particular reversible reaction. I give you the equilibrium constant Kc is 54.3 at a temperature of 430 Kelvin. At a point during the reaction, so this need not be at equilibrium. At a certain point, the concentration of H2 is this, I2 is this, and Hi is this concentration. Is the reaction at equilibrium? Okay. If Q is equal to K, then it will be, otherwise it is not. If not, what is the spontaneous direction of the reaction in this case? So what you need to do is of course go and calculate what is the QC value. Okay? It will be the concentration of H plus Hi raised to power 2 over concentration of H2 raised to power 2 over concentration of I2. You sum those values in. Okay? 5.5 square over 1.2 square times 0.66. Okay? Then you calculate what is the value of QC. Okay? And you will get 31.8, and the units is mole minus 1 PNQ. Okay? It is different from what you have in your notes. Okay. I'm not too sure when you calculate it. There is a mistake, huh? Alright, so Hi to power 2 over H2 over I2. Right, substitute the 2, there's no 2 here. It's H2 raised to power 1. Likewise, there's no 2 here. Oh, sorry, H2 have. Right, no, there's a mistake. Right, so follow what is in your notes, it is correct. Okay? Right, in your notes is H2 plus I2 give you 2 Hi. Okay, so there is no coefficient 2 here. There isn't a coefficient 2 here. Right? Okay? Right? After you calculated your QC value, okay, because I think we got it wrong over here, but your QC value should still be lower than Kc. Right? Because it is lower than Kc is not the same, the reaction or the system is not at equilibrium. Okay? The reaction will be spontaneous in the forward direction to increase the concentration of Hi and decrease the concentration of H2 and I2. Decrease until Qc is equal to Kc. Right? Once Qc is equal to Kc, you have reached dynamic equilibrium. Okay? And the system will stay at equilibrium. Okay, so you will proceed in the forward direction until equilibrium is achieved. Okay? Alright? Okay, so for today we'll be looking at mainly calculations that involve Kc, writing equilibrium, writing balanced chemical equations, find equilibrium concentration using ICE table, substitute into the Kc expression and solve. So we're looking at quite a few examples of calculations involving Kc and P. Okay, so let's take a look at example 4.2. Example 4.2 requires you to determine Kc from equilibrium concentration. Okay, so look at the phrasing of it. First, in a vessel, you have an initial concentration of H2I2 and Hi. Okay, if you see the word initial, that means it is at the start. Okay, so if it is at the start, shouldn't be at equilibrium. Right? The concentration of H2 is 0.10, 0.150 mole per dm cube when equilibrium is established. So when equilibrium is established, the concentration of H2 is this value. Okay? Ask you to calculate the equilibrium constant Kc for the reaction. This one. Okay? Right. So we will use this thing called the ICE table. ICE stands for the initial concentration. What is the change in concentration and what's the equilibrium concentration? Okay. Okay, so we know that the initial concentration is 0.750, 0.830, 0.110. Okay? Alright, so if you use three values, right? If you use these three values to calculate, you will get your Q. Right? You will get your Q value. We know that the equilibrium concentration of H2 is 0.150. Okay? Right? So from 0.750 to get to 0.150, what must be the change? The change will be minus 0.600. So that is the change. Okay? Alright, and that's where we need to be a bit clear what is happening. Initially, why are these concentrations these values? Okay? It is because of the person doing experiments using these concentrations. So this concentration can change depending on how much is added in or how much is mixed in. Okay? So this change here is the difference between the initial and the final, so minus 0.600. Now this change here implies that this concentration of H2 reacted, right? It took part in the forward reaction. So what must be the change in concentration of I2? It must be the same as this value, minus 0.600. Okay? Now this was one of the questions that was raised on Speedo. It is very confusing to the person who posed the question. Why are these values like this? And why are these values like that? Now if you look at the equation again, the change in concentration, the ratio of the change, is always in accordance to the balanced stoichiometric equation. Right? So if the change here is minus 0.600 moles per dm cube, this must also be minus 0.600 moles per dm cube because the stoichiometric coefficient is the same. If this amount reacted, it must result in the same amount being reacted. But the volume is the same, right? So that's why the concentration change is the same also. So 0.830 minus 0.600, you get 0.230. So that is the equilibrium concentration. So what is the change in concentration of HI? It will be positive, right? Because now we are favoring the forward reaction. It should be positive 1.2, correct? Okay, so it's positive 2 times 0.600. Okay, which is 1.2. So 0.110 plus 1.2, you get 1.31. Okay? Right, so Kc is equals to the concentration of Hi squared over H2 concentration over I2 concentration. So you will get 49.7. No units because all the concentration units will get cancelled out. Okay, so this particular Kc, no units. Okay. Right, can I give you 2 minutes to try out example 4.3? Okay, if there's any questions, just raise your hands and they will come and attend to you. question. And the question says you started off with 1.00 moles of sulfur trioxide. Okay? Was placed in a 2-liter vessel. This is where some of you experience a little bit of difficulty. 2 liter, we see it every day, right? You buy a 2-liter bottle of Coca-Cola. But 2 liters is also the same as 2 dm cubed. Okay? 2 dm cubed. So from this first sentence, you can determine the concentration of your SO3. This must be the initial concentration of SO3. The question seems to suggest that they only put in SO3 at the start. They didn't put in any SO2, nor did they put in any O2. Right? They only put in SO3. Okay? And let the reaction start. When equilibrium was reached at a certain temperature, the vessel was found to contain 0.540 moles of sulfur dioxide. Okay? Calculate with constant Kc for the reaction above. Okay? So the initial concentration of SO3 must be 1 divided by 2. 0.500 mole per kg. What is the equilibrium concentration of SO2? 0.54 divided by 2. 0.270 mole per kg. So this is the equilibrium concentration. So now if I put everything onto the ICE table, what is the initial concentration, what's the change, and what's the equilibrium concentration? 0.50000. Right? Because the question didn't say that it added in any SO2 or O2. So it must be 0. The equilibrium concentration of SO2 is 0.270. So the first thing that we can determine must be the change in concentration of SO2, which is plus 0.270, right? Okay? Which means that what must be the change in concentration of O2? It must be half of that value. Okay, so plus 0.135 mole per kg. Which means that the equilibrium concentration of O2 will be 0.135. And what must be the change in concentration of SO3? It must be minus 0.270. Okay? Because remember, what happens here is you can calculate your Q. It must be much larger than Kc. So the backward reaction will be favored. If you favor the backward reaction, to form 0.270 mole per kg of SO2, okay, you must have reacted with to form this concentration of SO2, 0.270, the same concentration of SO3 must have reacted because their stoichiometric coefficient is the same. Right? Okay? Which means that the equilibrium concentration of SO3 will be 0.230. So with these three equilibrium concentrations, I can substitute into the Kc expression, okay, to find out what is the value of Kc. So Kc units will be 5.38 Kc units mole minus 1 km cube. Okay. Right, so that's how we will find your equilibrium constant by looking at the change in concentrations of the either reactants or products. Okay, Anna? Okay, I'm going to run through example 4.4 with you all. Okay. Now example 4.4, the context is a bit similar, but there's just some things that's a bit different. In this case, for 4.4, if you read the question, they gave you amount again. 1 mole of methanol, 1 mole of methanolic acid react together according to the equation. Equilibrium mixture contains 0.200 moles of ester, okay, methyl attenuate, and 0.200 mole of H2O. Ask you to calculate Kc. In this case, you will have realized that unlike example 4.3, example 4.4 didn't give you the volume of the vessel. Okay? So if we wanted to find out what is the concentration, we will need the volume, right? Okay? So does it render this question unsolvable? Not really. Okay? Because when we look at this equation, you would find that the total number of reactant is equal to the total number of product. Okay? Which means that if I just let the volume be V, they will all cancel out. So I wouldn't be too concerned about the volume of the vessel. For this ICE table that I construct, I look at it in terms of amount first, in terms of moles. Okay? 1 mole, 0, 0. Equilibrium, I get 0.2 moles of the ester and 0.2 moles of water. Okay? So the change must be plus 0.2 plus 0.2. The change of the reactants must be minus 0.2 to give you 0.8 and minus 0.2 to give you 0.8. Okay? So when I let the volume of the equivalent mixture be V, because I need the total volume, I sub everything in. 0.2 over V times 0.2 over V over 0.8 over V times 0.8 over V. All the volume terms will cancel out. Okay, so I get 0.0625. No units. Okay. I don't have a V term in the end and they all cancel out when the number of moles of reactants is equal to the number of moles of product. Okay. Right? So that's for question 4.4, where we don't need the volume to solve. But if the number of reactants is not equal to the number of moles of product, then I must use the volume of the reaction because it doesn't cancel out. Okay? Right? So the V terms are cancelled out. This happens when equivalent mixture, when there is an equal number of moles of molecules on both sides. In that case, the equivalent expression is independent of volume. Kc will become unitless. Okay. Right, so the amount of substance can be used in the calculation of Kc. Right? So you should show the volume in your working, even though it gets cancelled out ultimately and doesn't affect us. Okay? So for 4.4b, okay, that's the amount of, sorry, in this case B, 2.00 moles of methanol and 2.0 moles of amino acid will mix together at the same temperature. Calculate the amount of methyl attenuate produced at equilibrium. Okay? 2 moles, same temperature. Okay? Let X be the amount of ester produced at equilibrium. So use the same ICE table again. Okay, 2200. Okay, equilibrium amount, let it be X. So you can see that this must be plus X. The increase in amount of water must be plus X also. Okay, so this will be X. Minus X for your alcohol. So you get 2 minus X. And minus X for attenuate acid, so you get 2 minus X as well. Okay? Okay? Then if you want to solve for X, what do? Substitute all of them in your Kc expression. Okay? And then solve. Okay. This was what you found from A. So now what you do is, you know that Kc is going to be 0.0625. Substitute all of the values that you got from your ICE table. All the V terms will cancel out. So basically you get Kc is equal to X squared over, open bracket, 2 minus x squared. Right? Then solve. Okay? You can take the square root of the whole thing is equal to the square root of 0.0625. You can solve for x. Okay? You want to expand and solve using quadratic equation, also can. Alright, so now we've been looking at, for the past two examples, those that involve KC. Okay? Alright? Okay? Now example 4.5, okay, right, looks at it in terms of partial pressure instead of concentration. So you have a reaction of SO2 with O2 to give you SO3. Okay. Then they give you 3.00 moles of SO2, 3.6 moles of O2, and 4.8 moles of SO3 were heated initially in the vessel. Okay, so these are the initial amounts of the three gases. The vessel contains 2.6 moles of SO2 when equilibrium is reached. The final pressure is 1.40. Okay, so this final pressure must be the final equilibrium pressure when equilibrium is achieved. Okay, in part A, asks you to calculate the partial pressure of SO2, SO2, O2, and SO3 at equilibrium. Okay, so you must find out what is the partial pressure of each of these three gases at equilibrium. Okay, so you will need your ICE table again. Right? Now, what do you know from the question? The question gave you the initial amounts of the three gases. Right? Okay? So you know it's 3.00, 3.60, and 4.80. Okay? You know that the equilibrium amount of SO2 is 2.6, which means you can fill in the rest from your ICE table. So this must be minus 0.40. Okay? Right? And now all of you all should tell me what is the change in amount of O2? It will be minus 0.20. Right? Okay, so you will get 3.40. What is the change in amount of SO3? This will be plus 0.40. Okay, so you will get 5.20. Okay, these are the equilibrium amounts of the three gases. We are very close to the answer, but we haven't really answered the question, right? And the question wants us to express it in terms of partial pressure. But what we have from the question is the final equilibrium pressure is 1.40 atm. So how can I express this amount into partial pressure? Okay. I will need to use a concept that we learned in gaseous state. Right? That total pressure times mole fraction is equal to partial pressure. Right? So partial pressure is equal to mole fraction times total pressure. Okay? So this was what we learned before. Partial pressure of A must be equal to mole fraction of A times total pressure. Okay? So total amount of gas and equilibrium, you need to add them all up. You get 11.2 mole. So this is a total amount of gases. So the partial pressure SO2 is the mole fraction times total pressure. O2 mole fraction times total pressure, mole fraction times total pressure for SO3 also. Okay. So you get 0.325 atm, 0.425 atm, and 0.650 atm. So these are the three partial pressure. You add all of them up, you will get 1.4. Okay, so this is for part A. Alright. Okay. Now part B requires you to from there on to find Kp value. So it will be very similar to what we've done in the previous examples. To find Kp, it is exactly the same as how you will express in terms of Kc, except that everything is done in terms of partial pressure. Okay. Right? Now something for you to know. Okay, partial pressure of SO3 squared, okay, I must highlight again because students tend to do this. When you are writing Kp expression, okay, we express Kp in terms of partial pressure of SO3. So PSO3. Can you don't go and confuse your examiners by using square brackets here? Don't use square brackets. Okay? Although I must regret every time I say don't use square brackets, because some of you all will think and process, he just said square brackets. When I tell my daughter, don't run, she will run. Okay? Don't be rude, she will be rude. Okay? Don't use square brackets, because when you use square brackets, what does square bracket represent? Square brackets represent. Square brackets represent concentration. So when you put square brackets here, you are confusing everybody because nobody will know are you referring to partial pressure or referring to concentration. Okay, so don't use square brackets. Right, then substitute your partial pressures in. Okay, you will get your Kp. 9.41 atm to the power minus 1. Okay? So that's for example 4.5. Right now, example 4.6. Okay? It is a variation of concept that they are not roughly about the same. Now, they ask you to determine total pressure for Kp and percentage dissociation. Right? So, let's read the question first. They give you a reversible reaction. Okay? They give you temperature 375 degrees Celsius at. So that's the promotion. Is everything okay? No? I know. Right, say no, right? Why? At this temperature, okay, I need you all to look at the question and be with me. At this temperature, and at an overall pressure of 1.01 times 10 power 5 Newton per meter squared. So this is the pressure. Okay? A sample of SO2Cl2 gas was found to be 84% dissociated. Now, from reading this statement, can you tell me what was added initially? What was added initially? Did I add in SO2Cl2? Or did I add in SO2 and did I add in Cl2? What did I add? I added SO2Cl2, right? Because that's what they wrote here. Okay? So my second question is, from reading this first sentence, have we reached equilibrium? From reading the sentence, have we reached equilibrium? I see some of you all shaking your head, some of you all nodding your head. Okay? Now if you think about it, just now what we said was that what the person did when carrying out this experiment was to put in SO2Cl2, right? When you put SO2Cl2 to the reaction vessel, a reversible reaction took place. Some SO2Cl2 reacted. React until it reaches equilibrium. So when you see that 84% has dissociated, have we reached equilibrium? Yes, we have. We have reached equilibrium. Okay? Right? We have reached equilibrium. Okay? So A, calculate the initial pressure of SO2Cl2. Because we have learned the ICE table, you can fill it in first. You added SO2Cl2, let the partial pressure be P first. Okay? Right? Now how do we fill in the ICE table? Okay? We know that at equilibrium, okay, 84% of SO2Cl2 have reacted. That means the change here must have been minus 0.84 P. Okay? Which means that at equilibrium, the partial pressure of SO2Cl2 will be 0.16. Okay? Right? Because at equilibrium, 84% of P would have reacted. So 84% of P is 0.84 P. Okay, so with that, you can fill in the rest of the change. This must be plus 0.84 P, so the equilibrium partial pressure of SO2 is 0.84 P. Okay? The change in partial pressure of Cl2 is plus 0.84 P, so the equilibrium partial pressure of Cl2 is 0.84 P. Okay? Right, so the sum of all the equilibrium partial pressure must be equal to the partial pressure of the total system. Okay, so if you add them all up, 0.16 P plus 0.84 P plus 0.84 P gives you the total pressure 1.01 times 10 to the power 5. So P must be equal to 5.49 times 10 to the power 4 Newton per meter squared. Okay. Now I want to go back to the phrasing of the question again. Now, I say again, when you read this particular sentence, they are describing to you a system at equilibrium. Okay? Russia's right. You have friend living at the rules here. Okay. Right, so from there you can calculate the equilibrium constant Kp for the above reaction. Okay. So take the partial pressures of the three gas, put it into the Kp expression. Okay. Substitute P in, you will get the value for Kp. Right, let's take a look at example 4.7. Okay, example 4.7, your nitrogen tetroxide, okay, forms an equilibrium reaction with NO2 gas. Okay, NO2 gas is a brown gas. It's one of the only few brown gases you will see in your A-level syllabus. Okay? Right, so at 26.7 degrees Celsius, 1 atm pressure, 20% of the sample of N2O4 is dissociated. So once again, they are describing to you the equilibrium system. Calculate Kp for the reaction. Okay? So once again, you can construct your ICE table. Okay? Let X atm be the initial pressure of N2O4. Okay? So the change in partial pressure is minus 0.8x. So the equivalent partial pressure of N2O4 minus 0.8x. Okay? So the change in concentration, the change in pressure of NO2 is going to be 0.4x, which means that the equilibrium partial pressure of NO2 is going to be 0.4x atm. Okay? The sum of equilibrium partial pressure equals to total pressure. So solve for x is equals to 0.833 atm. Substitute it into your Kp expression, you get 0.167 atm. Okay, very similar to what we saw in the previous part. Okay, right. Now the next part is something that we haven't seen before. They ask you to calculate the pressure that would be necessary at 26.7 degrees Celsius to increase the percentage dissociation to 30%. Okay? Right. Now, if you look at this temperature, 26.7, why did they bother to tell you 26.7 again? They are retelling you the temperature is the same so that they are telling you that the value of Kp never change. Because Kc, Kp only change with pressure. Only change with temperature. So if temperature never change, Kp, Kc wouldn't change. So this temperature is told to you to let you know that Kp never change. You can still use back the same Kp. Right? So now you need to let the initial pressure of N2O4 be something else. Let it be Y. Okay? Right, so in this case you want only 30% to dissociate. So now your change will be minus 0.30y. You will get 0.70y over here. You will fill in everything else. This will be plus 0.60 because the mole ratio is 1:2. Okay, so you get 0.60y here. Sub into your Kp expression, which has the same value. Okay? Kp remains constant at the same temperature and does not change with partial pressure. Okay? So you substitute your two values in for a Kp expression. This must be equal to 0.167 atm, which you calculated from A. So now you solve for y. Y is equal to 0.325 atm. Okay? But you must answer the question. What is the required pressure for 30% of N2O4 to dissociate. So it must be the sum of all equilibrium partial pressure, okay, which is 1.3Y. So substitute it in, you get 0.433 ATM. So when I change the pressure, okay, alright, I change the pressure, the percentage dissociation changes, right? But Kp never change. Okay, so I say again, for this question 4.7, what you can notice is that when you change pressure, okay, the percentage dissociation changed, but your Kp never changed. So Kp, Kc never changed except when you change temperature. Okay. Alright, so this is another method of finding the answer. So you let the initial amount of N2O4 be Z, okay, you get the same ICE table. Okay. You substitute everything in, but instead of using partial pressure, you just use mole fraction times total pressure, also can. Okay. Then in this case, right, you solve for P total because your Z terms will cancel out. Okay, you get a similar answer. So both answers are always slightly different, both will be fine. Alright, can I ask you to look at the last example, 4.8? Okay, I'm going to give you about 4 minutes to try out the question. Okay, if there's anything that you're not sure of, please ask. Okay, you will need to use your ICE table to find the answer. They want the degree of dissociation, alpha. Okay, and I tell you how to express degree of dissociation.
But you are not answering the question. What you complain is and it's what? But they want to degree of
Okay. Now we'll go through the answer together. Okay. Now actually this 4.8 example. Okay. Now I want to just highlight to you all that the first statement that was given to you all is meant to help you. Okay. What is happening is I give you this. I say let Y be the initial partial pressure of N2O4. Okay. And I let X be equal to the change in partial pressure of N2O4. Okay. Right? So if I just fill in this table using X and Y, this is what you're going to have. Initial partial pressure N2O4 is going to be Y, 0. I know that the equilibrium partial pressure of Y is 0.500 atm because that was what's given to me. Okay. The change in partial pressure is minus X, so this must be plus 2X. So the equilibrium partial pressure of NO2 is going to be 2X. Okay. So from this column here, I will know that Y minus X is equal to 0.500. Okay, so that's one equation. Okay. Kp, right, which is the partial pressure NO2 squared over the partial pressure N2O4 is equal to 2X floating squared over 0.500. Okay, and I am given Kp. So Kp is 0.725 atm. So I can solve for X, right? Okay, X is equal to 0.301. Okay. Alright, so this 0.321 atm, it is the partial pressure of N2O4 that reacted, that dissociated. So I'm going to use this value subsequently to find out what is the degree of dissociation. Okay? But before I can find the degree of dissociation, I need to find out what is the starting amount or starting partial pressure of your N2O4. So how do I do that? I use the first column of the ICE table. Okay? That Y minus X is equal to 0.500. So Y must be equal to 0.500 plus X. Okay? So Y is equal to 0.801 atm. So this is the initial partial pressure of N2O1, which is proportional to the amount of N2O4. Okay? So this partial pressure tells us something about the initial amount of N2O4. This partial pressure X tells us something about the amount of N2O4 that is dissociated or that reacted. So to find alpha, okay, it will just be X divided by Y. Just take this 0.301 divided by 0.801. You will get 0.376. So that is your alpha, degree of dissociation. Okay? So what we have seen is actually for a KC-KP calculation. We have seen a few examples so far. The question can give you changes in equilibrium concentration, give you changes in amount to reach equilibrium, give you percentage dissociation, or give you alpha, degree of dissociation. Right, ask you to calculate either KC-KP, equilibrium, change in concentration. Right, so we will stop here for today. Next lecture, we will look at the Chaptier's principle. Right? So any questions, please go on this video. Come and look at the Thank you.